Hey, welcome everyone, and thank you very much for coming to this research seminar from Energy Futures Lab on estimating the load balancing potential of households in the UK. So today we are delighted to have with us Dr. Shefali Khanna, whose research interests lie in energy and environmental economics and policy. Her current research focuses on understanding the drivers of energy demand in the residential and industrial sectors and on evaluating the design and impact of climate policies. She earned a PhD in public policy from Harvard University, where she was a pre-doctoral fellow of the Harvard Environmental Economics Program and a PhD student affiliate of Evidence for Policy Design at the Center for International Development. She received a BA in Economics from the University of Maryland, College Park. Today, she'll be speaking about the methodology that she and her group have developed to identify the extent to which electricity and gas consumption can be shifted. This methodology has potential for use by policymakers, energy systems planners, to inform the design of demand response programs. So I'll now hand over to the capable hands of Shefali to talk about this methodology.
All right, thanks so much. So I am a research associate in the Department of Economics and Public Policy at Imperial College Business School, and I'm also an affiliate of IDLES. I will be presenting our research, which sort of attempts to estimate the load balancing potential of households in the UK. I'll explain what I mean by that. This work is joint with Felix Bracht, who is a research economist at the LSE, Ralph Martin, who's here, associate professor of economics at the business school, and Mirabel Moulz, who is an assistant professor of economics at the business school, and is also a co-I with IDLES. So we're a group of economists, and that's sort of the disciplinary lens through which we approach the subject, but we very much welcome your feedback, comments, questions, as well as any thoughts you have on alternative approaches that we could think about as well. We definitely welcome your thoughts. I had presented this work at the IDLES conference in the fall last year, so apologies if some of you are seeing this again, but hopefully it's still relevant and interesting. Okay. All right. So the transition to a net zero carbon energy system in the UK really cannot be achieved without widespread behavior change in patterns of energy use, as well as sort of a radical stepping up of public and private investment in the energy sector that includes in renewable energy and transmission capacity, electrification of heating, transport, as well as investments in energy efficiency. At a more fundamental level, understanding the energy consumption choices of consumers will be critical to inform the design of policies that can induce this sort of behavior change and scale up the adoption of emissions reducing technologies. Some examples of choices that consumers make on a daily basis in this regard include deciding when to use energy for heating and cooling, which is going to be a focus of much of my presentation today. Taking public transport instead of using private vehicles, investing in retrofitting and other energy efficient appliances. Now, economists have documented various market failures, including most notably the lack of globally uniform emissions pricing, as well as behavioral biases such as inattention to cost savings that might accrue in the future from investing in an energy efficient product today. And how these might sort of induce consumers to make suboptimal choices. So I think it's really important to think about, how to design policies that can not only internalize externalities, but also potentially nudge consumers to make decisions that are broadly consistent with the goal of decarbonizing the energy system as quickly and as cost effectively as possible. Okay, so this talk is going to focus on demand flexibility, which, as you all know, is about incentivizing consumers to shift their energy demand so that it aligns with supply, which would help balance a grid with large amounts of variable renewable energy. And so the question is, how do we encourage demand flexibility? Well, the rapid deployment of smart meters certainly gives us a lot of visibility into households' energy use patterns. And the project that I'll be presenting today uses data from smart meters for large samples of residential consumers in the UK. But smart meters can also be used by utilities to introduce various forms of dynamic pricing that can be leveraged to incentivize consumers to shift their energy consumption to times when prices are low, which will typically also coincide with times when there's more zero carbon energy available on the grid. Furthermore, the returns from dynamic pricing could be even larger for consumers that have made complementary investments in decentralized technologies such as rooftop solar combined with batteries, say in a Powerwall or in an electric vehicle, given that these consumers are now even less dependent on the grid for meeting their energy demand, and they could potentially earn a high return by selling their surplus energy back to the grid when prices are high. And finally, to the extent that these incentives could reduce peak energy demand, they could also lower the average cost of power procurement, since utilities often forward contract additional generation capacity to meet the expected demand of a small fraction of the hours in a year. And so to the extent that these incentives reduce peak demand, they could lower the average cost of supply and also lower retail prices for downstream consumers. Now, estimates of the impact of these sorts of dynamic pricing programs on energy demand is somewhat mixed. There's the recent Crowdflex study, which was carried out by about 5 utilities in the UK, which offered time of use tariffs to about 25,000 households and found that these pricing signals alone could reduce peak demand by up to 23%. But other studies that have been carried out by economists in the US and other contexts find that households may be inattentive to electricity prices, and that could dampen the behavioral response to these pricing signals. And so these studies point to the need to use automation technologies for energy demand management, where households' energy use sort of responds automatically to changing pricing signals, for example. And these studies show that small changes in energy demand induced by these automation technologies could actually result in sharp supply cost reductions. And my research team at Imperial is in fact also doing some experiments with these automation technologies and seeing sort of what the scope for flexibility in energy demand is, and how it can sort of be enhanced by these technologies in the context of the UK, but also in India. Okay, and finally, there potentially concerns around safety and data security, which may impact the adoption of these devices, and this is an area of ongoing research as well. Our work today is going to focus on measuring the underlying load balancing potential of households in the UK. And this is important because it would sort of help us think about how these pricing incentives as well as automation technologies should be targeted. For example, if you have a household that has a high load balancing potential at a certain time, then they may not be it may not be necessary to give them a high incentive to sort of shift their energy consumption at that time versus a household that has a low load balancing potential. Okay, so recent studies, particularly in engineering, have attempted to identify flexibility potential using machine learning methods. So clustering is a common unsupervised learning technique that essentially groups households into clusters based on historical patterns in their energy use to try to identify when their energy demand is likely to peak. Typically, they identify flexibility potential by taking the difference between the centroid of the cluster, which is the red line in these figures on the right, and the household's actual energy consumption, which is the green line. So that difference gives you sort of the measure of flexibility potential. Now, while clustering techniques are a highly flexible way of modeling energy demand because they make no functional form assumptions, there are some important shortcomings of this approach. So, there could be a valid reason why a household in a given cluster is consuming above or below the centroid that has nothing to do with its flexibility potential. And so we think it may be important to consider modeling individual and local characteristics as well, which is something that clustering approaches fundamentally don't do because they're non-parametric. Furthermore, if you exclude some observations, that could dramatically change the number of clusters as well as the composition of the clusters. So these techniques typically are not very robust. And finally, there are no off-the-shelf methods available to sort of validate clustering techniques that we know of. Instead, we propose two alternative approaches, which are both quite different. The first approach uses the energy consumption response to changes in weather using hourly observations of households' energy consumption, which we get from the smart meter data. And the second approach uses the residual variation in models of baseline energy use or non-shiftable energy use as a measure of load balancing potential. And I'll get into these two approaches in more detail. But the data sets that we use include smart meter interval data for electricity and gas from two separate sources. So we have data from Octopus Energy, which covers about 1,600 households for 2 years, 2019 and 2020. We do have some information about household and property characteristics as well from this data. But we more recently acquired a much larger data set from the Smart Energy Research Lab, which covers about 13,000 households starting in 2019. The Smart Energy Research Lab is a consortium managed by UCL, and it includes sort of a detailed household enrollment survey that covers the types of appliances that households own, as well as patterns of use. And we also have EPC reports for about half of the households in the Smart Energy Research Lab. Most of the analysis that I'll be showing today uses data from Octopus. We also have hourly high-resolution weather measurements from ERA5 land satellite data. So the way we link the weather data with the smart meter interval data is as follows. We basically first match the postcode centroids, so the centroids of postcodes with the closest ERA5 coordinate. And because our smart meter data from Octopus only has the outcode as sort of the location identifier, we average the weather observations across postcodes within each outcode. So the outcode is the lowest unit of geography that we observe for households in the Octopus data. It's just an aggregation of postcodes. Yeah. So let me show you now some sort of descriptive figures that we created using the smart meter data. So this figure on the right shows you the hourly electricity and gas consumption of an average household in our data. As you can see, electricity consumption sort of peaks in the mornings when people, use. Electricity consumption doesn't peak in the morning. Electricity consumption increases, then plateaus, peaks in the evening. But gas consumption peaks in the morning when households, turn on their water heating for showers, presumably. It then peaks again in the evening as people return home from work and turn on their lights, stoves, heating and cooling devices. Okay, so we now bring in sort of the spatial dimension, the spatial sort of heterogeneity that we observe in electricity and gas use. So these figures, or animations, I should say, show you the average hourly electricity and gas consumption at the outcode level. Again, outcode being the lowest unit of geography that we observe for households in the Octopus data. And as you can see, there's quite a bit of spatial sort of heterogeneity here. We see, households' energy consumption peaking at different times in different places, which could also suggest that, maybe households can be flexible at different times depending on where they live. We also get a sense of sort of the spatial coverage of our data, which we think is relatively good. Okay, so the first approach for measuring load balancing potential uses the energy consumption response to hourly changes in weather. And this approach is really premised on the idea that the demand for heating is, largely going to be driven by changes in weather. And so what we do here is we take 750 randomly selected households from our data, and we run household-specific regressions of electricity and gas consumption on a series of binned weather variables. So we have 26 temperature bins of 1 degree Celsius each, 18 precipitation bins of 100 millimeters each, 13 wind speed bins using Beaufort scale categories for wind speed, and then 13 relative humidity bins of 5% each. And we omit one of each of these bins in our sort of regressions in order to sort of identify the effect of having an additional hour in each of these temperature bins relative to the omitted category. And sort of the idea here is that, we're trying to sort of construct this detailed picture of the conditions under which households' energy demand sort of responds to weather changes in order to give us a sense of where there is flexibility potential in the system and where we should be sort of targeting these incentives for load balancing, whether that's through pricing or through automation. Okay, so these plots now kind of illustrate the coefficient estimates from these regression models that I just mentioned. So the bottom left axis sort of sorts in households based on their energy intensity, so their average electricity and gas consumption in the data. The bottom right axis has the temperature bins. So as I mentioned, we, for these regressions, omit one of the bins, so that's the one in the middle that you see there. So our coefficient estimates are going to be relative to that omitted category. The y-axis has the coefficient estimates on electricity and gas consumption of having an additional hour in each of these temperature bins for a household, for a household in one of these energy intensity bins. And so as you can see, electricity and gas consumption, are both sort of more responsive at extreme temperatures, which is what you would expect. People turn on their heating when it's too hot, when it's too cold, and they're cooling when it's too hot. We see that the effects are slightly more pronounced for more energy intensive households, right? So that's this cluster here. And that makes sense because heating is probably a large share of their energy consumption. The effects of gas consumption on temperature are sort of much less noisy, right? Because it's more driven by temperature. So you see a sharp kind of positive consumption response at low temperatures and a sharp negative consumption response at high temperatures. We then look at precipitation. So now we have on the bottom right axis the precipitation bins instead of the temperature bins. And what we see here is that, again, at high levels of precipitation, we see a sharp positive electricity and gas consumption response. This is in large part going to be driven by people spending more time at home when it's raining outside, and we see not much of a response at low levels of precipitation. But again, this is slightly more concentrated for more energy intensive households. Strong wind speeds also appear to drive electricity and gas consumption, regardless of sort of the energy intensity of the household. Again, we think, like precipitation, this is going to be driven by people spending more time at home when wind speeds are high. Okay, so then we sort of explore heterogeneity in energy consumption response to temperature by the time of day. So in order to do this, we run hour-specific regressions of electricity and gas consumption on the binned weather variables I described earlier, but this time we interact temperature or the temperature bin with each hour to explore this sort of heterogeneity over the time of day. And we include household fixed effects, which are basically dummy variables for each household that net out any sort of the effect of kind of time invariant differences across households. For example, maybe some households are larger than others, some are, have more sort of more people, more occupants than others. And so these household fixed effects are going to absorb the effect of those differences. Okay. All right, so now these figures have the hour of day on the bottom left axis and the temperature bins on the right axis. And again, we've normalized the sort of middle temperature bin that you see there. So the coefficient estimates kind of now tell us how energy consumption responds, to it, sort of having an additional hour in each of these temperature bins at each hour of the day. So as you can see, for electricity at low temperatures, we see sort of an increase in the morning, a plateau in the afternoon, and then electricity consumption peaks in the evenings. Whereas for gas, we see a peak in the mornings, which again is driven by possibly water heating for showers, and then again, a peak in the evening as people return home from work and turn on their heating. What's interesting is that we observe a sharp negative electricity and consumption and gas consumption response at high temperatures in the evening hours, which we think is probably driven by people, going out to dinner or just generally staying away from the house on hot summer evenings. Okay, so far I haven't really spoken much about how we're thinking about load balancing potential. So load balancing potential we define as sort of the sort of share of households' energy consumption that can be explained by weather in this sort of paradigm. And so this is using the household-specific regressions that I mentioned we ran for those 750 randomly selected households. And so here we're plotting histograms of the R-squared, which is a goodness of fit measure that tells us, how much of the variation in the dependent variable is explained by variation in the independent variable, which in this case is going to be sort of just our weather bins. So what you can see here is that weather explains a lot more of the variation in gas consumption than it does electricity consumption, right? And that makes sense because most households in the UK use gas boilers for heating. And so this kind of lends support to our premise, which is that the demand for gas is really going to be driven by weather. Yeah, so for electricity, it probably explains somewhere, less than maybe 10%. Weather explains less than 10% of the variation in electricity consumption, whereas for gas, it's somewhere between 10 and 20% on average. Okay, so we wanted to, sorry, too many events. Okay, sorry about that. So we wanted to sort of unpack these results a little bit more, and so we then run these regressions separately by season. So these figures illustrate the share of gas consumption that's explained by weather separately for 4 seasons: autumn, winter, spring, and summer. And so what you can see here, this was a little bit puzzling to us when we produce these results, is that it appears that weather explains more of the variation in gas consumption during autumn and spring compared to winter, which is when people generally use gas for heating. And so we also find that the standard deviation of temperature and other weather variables is actually higher in autumn and spring, right? So there's more hour-to-hour fluctuations in weather, which may explain, this pattern where people are actually more actively turning on and off their heating in the autumn and spring, whereas in the winter perhaps they just, leave it on. again, that sort of depends a little bit on whether they have a thermostat, which is sort of automatically adjusting the temperature relative to the weather outside. But in general, that might explain this pattern where you see households actively adjusting their heating demand in the autumn and in the spring when there's more variability in weather, and not doing so during the winter and summer. But this is, again, something that we do need to sort of investigate further. We then run these regressions separately by season and by time of day. So again, it's showing you the distribution of the R-squared, or the share of the household's energy consumption that's explained by changes in weather, separately for different times of the day. So on the top panel, we have morning, afternoon, evening, and nighttime hours for the autumn season. In the bottom panel, we have morning, afternoon, evening, and nighttime hours for the winter season. And so here it appears that it's mostly that weather is driving the sort of variation that we observe in gas demand in the daytime hours, and less so at night, whereas we don't observe much difference across time of day in the winter months. We then look at correlations between this R-squared, or the share of households' gas demand that's explained by weather, with property characteristics. So as mentioned, we have some property characteristics in the octopus data. So we look at sort of the correlation with floor area. Again, this is morning, afternoon, evening, and nighttime hours in the autumn season, which is when we see weather explaining more of the variation in gas demand. And we see this positive correlation, which is what one would expect, right? So households that are larger are probably more energy intensive, probably use a lot of heating, and heating comprises a larger share of their total energy demand. And so, yeah, we would expect this relationship. We also see a positive correlation with property value. Again, households that have higher property value are also ones that perhaps use a lot of energy for heating. Okay. Let me turn now to a second approach that we use for measuring load balancing potential, which is quite different from both the weather shocks approach that I just described, as well as the clustering methods that we showed you, that I discussed in the beginning. So here we define, household energy use in each hour as sort of the sum of baseline or non-shiftable energy use, and an idiosyncratic energy use that can be sort of shifted over time. So we attempt to model baseline energy use as a function of local features of the region where the household is located, such as weather, traffic, etc., energy prices, individual characteristics like income, amount of time household members spend at home, property characteristics, including the size of the house, the type of heating system, appliance stocks, etc. And so we predict electricity and gas consumption using models that take as covariates the weather variables, the household dummy variables that absorb the effects of time invariant differences across households. So that would include individual and property characteristics, as well as postcode area by time dummy variables, which basically absorb time varying covariates at the postcode area level. So that would include, for example, traffic, energy prices. And then the residuals from these models give us a measure of the deviation from baseline energy use, which is what we interpret here as our measure of load balancing potential. So let me illustrate this kind of method through an example. So here we take a randomly selected household, and the blue dots here are the values of their hourly electricity consumption over a 3-month period from June to August 2019. The red lines are our model's prediction of this household's baseline energy use. Now, the difference between the blue dots and the red lines is the part of their energy consumption that is perhaps more idiosyncratic. So that's the epsilon in that equation up there, and it tells us, well, this is kind of the alternative approach that we use to interpret load balancing potential. And I'll explain, the sort of pros and cons of these approaches shortly, but this is sort of, how we're thinking about load balancing potential here. Okay, so you might think that whether or not someone is present at home is going to be an important driver of their baseline energy use. Now, this is not a variable that we observe directly in our data, but looking at this figure on the previous slide, we actually kind of thought about an idea that we could implement to sort of develop a proxy for whether or not someone is present at home. If you look at this household's energy consumption in the month of August, you might notice that there's very little hour-to-hour variation compared to other months. And so it appears that that household is perhaps on vacation or generally away from the home. And so what we do is we develop a procedure where we first identify the day when the standard deviation of household energy consumption is the lowest within a given season and a given year. We then create a binary variable that equals 1 if households' hourly consumption is greater than the 99th percentile of energy use on that day that we've identified in step 1. Right, and so this gives us a sort of proxy indicator for whether or not someone is likely to be present at home or not. And when we kind of throw this variable into our regression as a covariate, we find that the prediction of a household's baseline energy use improves substantially. But what that means is that the sort of part of the energy use that's idiosyncratic is now going to be smaller. And so, it sort of, reduces the sort of load balancing potential of the household in the way that we're sort of interpreting it here. And I think there's an important difference, of course, between this approach and the one that we showed you before, which is that, here household, so the presence of household members is going to be an important driver of the household's baseline energy use, or the non-shiftable component of its energy use. And so the load balancing potential is now effectively smaller, whereas when we looked at the weather shocks approach, whether or not someone is present at home is going to be a strong driver of the energy, how their energy consumption responds to changes in temperature. And so ultimately, we need to think about ways of sort of reconciling these different approaches. And we very much welcome your feedback and thoughts on that. Okay, so now we plot sort of the distribution of the standard deviation of the residuals for a randomly selected sample of 10 households. So these are residuals from the model of electricity consumption. And so what this is telling you is it's giving you a sense of the part of the household's energy or electricity consumption that's more idiosyncratic, right? So if we compare the different seasons, we see that consumption is slightly more idiosyncratic, in the winter compared to the summer, and that could just be, driven by sort of more variability potentially in weather conditions. We find that consumption is less idiosyncratic during the daytime hours compared to the evening, which makes sense again because there's probably more variability in how many people are present at home in the evenings compared to the daytime. And for the same reason, we see more idiosyncratic consumption on weekends compared to weekdays. All right, so using this definition of load balancing, we think that load balancing potential would probably be greatest in the evening hours in sort of the colder months. And I mean, the reason that we focus on electricity for this analysis and not gas is because gas consumption is almost exclusively driven by weather. And so if anything, if we try to predict baseline gas demand, the prediction would be even tighter. And so that would imply even smaller residuals and therefore lower load balancing potential. Okay, I'm going to quickly summarize what we've shown you so far, and then I have some discussion questions. So hopefully that'll, spur some more discussion. So weather changes appear to explain most of the variation in gas consumption that we observe relative to sort of electricity, and this is especially pronounced in the autumn and spring seasons compared to the winter and summer. Again, we expect that this could be driven by households basically leaving their sort of their heating on during the winter, whereas they're more actively kind of adjusting it during the autumn and spring seasons, although of course that depends on whether they have a thermostat or not as well. Residential load balancing potential appears to be largest for more energy intensive households and is sort of concentrated during times when there are more people present at home. So this is something that also should be considered when we're thinking about how to target incentives for incentivizing sort of greater flexibility. Okay, so the point of this exercise is really to explore heterogeneity in the energy consumption response to temperature across households and time of day, to identify where there exists flexibility in the system and where the largest gains can be made in terms of incentivizing flexibility. So one of the questions we have for you is sort of thinking about, which of these approaches do you think could be more instructive for understanding where flexibility lies in the system? So just as a kind of reminder, the first approach, which looks at the energy consumption response to weather shocks, sort of, assumes that how consumers' energy consumption responds to weather conditions is sort of shiftable, right? And in fact, that could basically just be a reflection of their temperature preferences. And who knows, maybe that's not sort of adjustable over time. The second approach, which uses the residuals from the model of baseline energy use, might also be problematic if you think that the part of energy use that's idiosyncratic is also not necessarily flexible. So for example, a household might have a party on a weekend, and the energy consumption that for that time may not necessarily be flexible, but in the way that we sort of define energy potential of load balancing potential here, that entire sort of idiosyncratic energy use is considered flexible. And that's, I should say, similar to sort of the clustering techniques that have been used before, although of course the difference is in clustering, it's a completely non-parametric approach. And so, yeah, and whereas here we're kind of using this model where we're sort of trying to explain as best as we can baseline energy use using covariates. Okay, so I don't know if anyone has any thoughts on the first question. Yeah.
So just like when you've written up the temperature change with heat is electrified, that also doesn't take into account electric cars or electricity batteries. There was no way of dividing that, that you could have the individual specific amount, which is so it's, you can do anything in that one.
Right, so
define it without understanding the grid. Grid doesn't understand.
Right. So I think coming back to your first point about prices, that's certainly going to be an important determinant of a household's ability to be flexible.
No, it wasn't about households, it's about how you define energy personally. Because is energy a kilowatt hour, or is it a day? What I'm saying, because it changes depending on the tariff.
Yep.
How you define energy.
Yeah. So, I mean, we're trying to really understand household preferences here so that we can, then say, if we understand sort of, when people sort of need to use electricity or gas, let's take gas, for example. If we were to sort of electrify heating, how would that change the sort of, amount of flexibility that can be leveraged from the demand side? So that's kind of where we're going with this.
I see chip plants all over the grid using gas to make electricity. I also explain tariffs and government incentivized electric cars, which all people are being charged more than their little bit. Because there isn't a baseline. There should be a, if you live in an old house, still working with electric, where other people, like research doesn't count in bringing incentives and such. Try and ask the Green Deal or anyone like that how much electricity is used by researchers advertising. And the clue, it's just the domestic market. It seems
So I think your comment maybe relates a little bit to the last question I have here, which is basically, where should we target these kind of long-term investments in electrification? So replacing gas boilers with heat pumps or, other sources of, electric radiators, storage heaters, versus sort of targeting short-run incentives for load balancing. Right? And so that's something that this is basically what we want to do with this project, is that, try to map out where there is potential for leveraging flexibility among domestic households. And you're right, this is definitely going to depend on sort of the socioeconomic level of the household. So households that are higher income have higher property.
people living in homes and part government spend some of their money research, but that was asking to control that market, that part of it. But the non-immediate supplies of money cannot be looked at. Just the domestic market, what your data is about, what Oxford told you, with dozens of other electrical small companies, cheap bills, and bust. Clearly their data was for a reason as well. It's honest.
And I think it's not about the why the problems of the electricity market. It's really to see in this data what part of the consumption could be flexible. So I mean, basically, you probably have at home a fridge and you have a TV. Now, you would be very upset if people suddenly switched off your for load balancing, but probably wouldn't be bothered so much about your fridge. So, we were just trying to see from the smart meter data how much can you figure out about what fraction of the consumption is from fridges versus. So that is basically the objective. And then we can use this information if we succeed in this first step in sort of saying, okay, if we now find some way of automating this, or maybe we introduce some real-time pricing, then we might be able to shift 80% of that household's consumption on this particular day, and maybe another day it's only 10%. That's the objective here.
Shift the energy.
Well, the
Why do you ask the government what quality variables are there to sort of govern.
I'm not sure, but I mean, our focus on gas here is sort of the idea about hopefully in a couple of years, most of that will come from electricity, right? We're shifting to heat pumps and things like that. Okay, but that's the objective, right? We want to electrify heat. Once we have electrified heat, then we can use some of that for load balancing.
I would just take this moment to.
I was just wondering. I mean, electricity. There's a very high cost to peak hour demand, and if you can save 23% of peak hour demand, then that's a very significant saving. But gas at the moment, as far as I can see, the important thing is whether we get the average supplies to meet demand, and whether it's you don't have to pay any more for gas, and nobody's ever proposed you pay any more for gas in peak hours than any other time, because the distribution network and the storage is very easy and can cope with it either way. So I assume you're only interested really in gas use for heating when it does become electrified.
Exactly.
Yeah, but you missed out well, in terms of the words electric car charging, which is from a smart meter, it's very easily identifiable. And there's some other big loads which are very easily identifiable. But there's a project underway at the moment, and I signed up for it, where basically you're in line for £1,000 prize if you can reduce your usage at defined peak hours coming up, which they tell you about in advance, between 5:30 and 6:30. I suppose it could be other times as well in the evening, but so far the only ones that they've done are like that. And that's relatively straightforward. I the other day, I wasn't really expecting to win the money, but I thought I should do it. So I went round and I switched off all the sky boxes, which about 10 watts each. I switched off the Alexa Echo Show and stuff like that. Everything I could think of, I switched off, and I got it down to about 1/3 of a kilowatt. And they said you save something like 30-odd% in a note later, based on the smart meter. And they said the guy that, no, I think they said a bit more than that, but the guy that won it, because it was a random draw, saved less than I did in the end. But that seemed like a very worthwhile thing just for that 1 hour. And, if the aim of the game is to make sure that in the really critical hours, people do save electricity, then, it needs to be a very focused thing to get them to do that. And maybe a manual thing, whereas a lot of the approaches here are to do, more to do with, can we do it automatically? And when you move over to, I'm sure this is nothing that you don't know, move over to electric car charging, it's very obvious that you should be doing it on a flexible basis, controlled by the grid. You plug in overnight and the grid decides when it should be done. And similarly with heat pumps, for the higher, the bigger houses, they've almost certainly got room for some sort of heat storage, albeit for only maybe 12 or 24 hours. Just a tank of water would do. And then the whole process can be automated, so that if the grid says we really don't want to spend, we really don't want to satisfy heating demand now, you can defer that for a couple of hours, use heat from the storage and stuff like that. So in a sense, I mean, the problem is about getting the higher demand electricity houses to implement these investments. Well, actually, that's what it says at the bottom, to target those investments. But it doesn't necessarily apply to people that haven't got much money. It probably applies to people with the bigger houses that do have a lot of money. And therefore, there's more hope that you can do something very significant from it. That's what I feel here.
Yeah, let me just answer that, and then we can move to the other question. So you're absolutely right. I think there's a lot of scope for leveraging flexibility through EV charging and heat pumps. We currently don't have, well, actually, I think we do have data from West Sussex. From one of the kind of city councils in the UK on.
But if there's electric car charging going on in these houses, you would see it. I mean, it goes up, consumption goes up by 3 to 7 kilowatts, depending on how fast the car comes on charge. So it's very, very obvious.
Yeah, I mean, that's definitely something that we should look into. We are kind of thinking about approaches for disaggregating demand and seeing how it's sort of driven by different end uses. So that's definitely something we should look into. But yeah, I think your point about, looking at sort of the rationale for looking at smaller consumers, smaller households that say don't have, I mean, I think it's still worthwhile because ultimately, all of that flexibility could be aggregated. And so I think there's still a rationale for sort of, looking at how flexibility varies, potential varies across the board. Of course, you're absolutely right that it's going to be.
I think the issue is that the guys in the big houses are going to go to afford the big houses. So if you want the guys in the small houses to do it, somebody else has got grants or whatever.
Exactly.
To ensure they can do it.
So that's really the purpose of this exercise. It's to say, how can we sort of measure the underlying load balancing potential of households so that we know where to target incentives, right? If it's true that the smaller consumers just have very low, load balancing potential, then that would mean that we would need to give them a much larger incentive to shift their consumption. Whereas, you could also make the argument that for large households, because their energy consumption is perhaps very insensitive to the price, if their demand is more inelastic, then again we would need to give them sort of a much larger incentive to shift their consumption. So maybe we want to target incentives to households that are somewhere in the middle. But yeah, I think those are all great points.
Yeah, I just wanted to have a little kind of like answering the questions. I think that the first approach to me is kind of like, because I mean, temperature or weather in general is not going to explain many things that are kind of like inherent to kind of like maybe let's say more cultural or like personal characteristics that do not vary much. There's like all this work which is related to the point that he raised a moment ago is flexibility potential, right? And it depends on kind of like not only economic factors such as household size, income, blah, 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 but also gender, occupation, time at home, which were captured more in the second approach, if I'm not mistaken. So to me, the first approach could be potentially like valuable when you're actually doing not prediction, but baselining in the past. So basically when you already have the consumption, kind of like calculate the baseline, and from there you can actually measure how much flexibility was provided in the past. I think that would be more of a proper approach for baselining rather than load prediction. Whereas the second one, I think that it includes more of these, let's say, ancillary characteristics based on not only income but also other kind of like societal factors that could be very interesting for load kind of like prediction. So that would be kind of like my answer to the first question, based also on kind of like some findings on CrowdFlex that you already mentioned as well, and so on. I can expand on this if necessary. Then the second one, I actually don't really get the question.
Yeah, that's actually because I didn't explain it.
Yeah.
Yeah, so we've also sort of been thinking recently about sort of, load balancing as a discount rate. So this is sort of drawing a little bit from the behavioral economics literature where, you sort of try to estimate a discount rate between, money now, money later, the several, kind of choice experiments that have been conducted to elicit those parameters. And so we're thinking of basically applying a similar approach to thinking about load balancing, where households are effectively trading off immediate consumption versus delayed consumption. And so again, you can think of a household that has, say, a high discount rate, where they place a large discount on energy consumption in the future, having a low load balancing potential. And so perhaps they would need to be given more incentive to shift their consumption than a household that has a low discount rate. Mm-hmm. So that's sort of a kind of an alternative way of approaching this this topic, but it does require, yeah, I guess a sort of different methodology in terms of actually eliciting those parameters.
So very immediate thoughts on this one. For example, with the results that we have gathered from Crowdflex as well, you can see that when people are told to kind of like reduce their consumption in that.
Are you involved with the Crowdflex study?
Yeah.
Oh, okay. Good.
So basically you can see that you have energy reduction during the period that you're asking for the flexibility, but then you don't see that much of a rebound effect. So basically, I think it's more difficult to communicate to people this type of incentives because, for example, time of use tariffs are already very straightforward. But like, since you don't have that much information compared to these kind of like incentives that are appearing now that basically say, if you turn off tomorrow between 4 and 5, you're going to get this amount of money.
Yep.
That's very straightforward and people understand it very well. But for example, time of use tariffs, they are there, like most of the people have them, but then behavior doesn't change that much because they are just not aware of that variability, or if they are, they just don't care that much over time. So I think that, well, that could be kind of like a point of debate, but yeah, it will involve like a lot of active communication to the customer.
So this is actually a separate study that we're doing right now, where we actually give people, the sort of these smart technologies like Wi-Fi enabled smart plugs, and we give them incentives for these switch off events where an algorithm just turns off the supply of electricity through the plug, and we sort of vary the incentive. We send notifications before the switch off events, and we vary the amount of notice time that we give them. So that's definitely something that we're thinking about as well, and also kind of comparing just the time of use, so the sort of just the dynamic pricing incentive with sort of the automation where just to see, in one case we're sort of just reducing, we're reducing cost by just giving the incentive, the pricing incentive. In the other case, we're potentially deriving more benefits because we're relying less on effort or attention on the part of the household.
Okay.
So that's something that we're doing separately. But again, this project really focuses more on, how can we even think about efficiently targeting those types of incentives based on the underlying sort of potential for flexibility that we can observe using data from the smart meters.
Yeah, I mean, like in the.
Just going to give it back to the host because we're very close to time. So do you want to take more questions or do you want to follow up?
Happy to take one more question.
Okay, sure. Last question, sir.
Well, a general question is that I think of consumption in terms, reading literature a very long time ago, discriminatory and non-discriminatory. I mean, a lot of households, for example, aren't in a position to do what a middle-class household like mine can do, which is change the way that you generate heat or change the boiler, whatever. Maybe they're living in rented accommodation. So I think that, and you're focusing only on discriminatory consumption, I think. You're looking only at how people can, in their daily behavior, change the amount that's consumed. But the idea of discriminatory and non-discriminatory is that there's a lot of it over which they have no control. And I suppose related to that is, would it not be worth comparing housing stock that's properly insulated with housing stock that's not insulated, which seems to me the one biggest factor in determining what your heat consumption is? Because yeah, you can do what we've all been doing this winter, which is turn it down as soon as you go out of the room because suddenly all the prices have gone up. But insulation is a much bigger factor, and that's outside a lot of people's budget and understanding.
Absolutely. And so that's actually going to be reflected in, so the differences in the quality of insulation will be reflected in how sort of energy consumption responds to changes in weather, for example. So that is included effectively in the estimates. That's something we could definitely test, because you're right, we do have the EPC data as well, so we could see how, yeah.
one comment, and that is that if you look at UK electricity now, it's going to go to then you can almost forget what we use electricity for the movement, and just concentrate on EV charging and the transfer of gas boilers to heat pumps, because that's going to double electricity demand now. So, you know, I guess that helps.
That's exactly where we're going with this. Yeah.
That already though, but that really says you've got to concentrate on the big things. And electric vehicle charging, you don't have much data. And then gas.
Yep. Yeah. So we won't have much. Yeah. Exactly. We don't have that many households that have EVs, but we certainly want to essentially take our estimates of the, you know, how gas consumption demand responds to changes in weather, and try to extrapolate what would happen if we were to electrify heating. But we could also think about how to do this for EV charging as well.
I think we are pretty much bang on time now, so thank you all very much for coming today and for your engaging discussion, and particular thanks to Dr. Shefali Khanna for an excellent demonstration of this methodology. So thank you.
Thank you.